Okay, we're going to start out in section 5.1. We're going to be approximating areas under curves by a couple different methods. So if we have, say, a random curve like this, first what we're going to look at is something called the right endpoint approximation. So what that'll do is basically we'll say we want to approximate starting at A and stopping at B. We're gonna break the interval up into a bunch of evenly spaced parts, and then we're going to use the right endpoint to create some bars that we're going to kind of use rectangles to approximate, and say that this rectangle here approximates the area of the function under that region of the graph. So we'll go up with this to set the endpoint of that rectangle. This right here will go up, hit there, set the endpoint of that. So we're using the right endpoints to create these little rectangles. They're supposed to be the same spacing between them, but I've kind of drawn it badly. And this would be what we call a right endpoint approximation. So we're going to focus on that type, a left endpoint approximation and a midpoint approximation. So say we had a similar type curve from A to B. A left endpoint approximation, again, you would break your interval up into evenly spaced units. But instead of going and letting the right endpoint of each of these rectangles fix the height of the rectangle, we're going to go and let the left endpoint of each rectangle set the height of each of these rectangles. And then what we do is we then find the area of all those rectangles and we add that area up, and that will be kind of close to the to the actual area under the curve. So this would be a left endpoint approximation. And the third one we're going to look at is going to be a midpoint approximation. So right now we're just trying to give you an idea of how we can kind of use these to calculate the area under the curve. So we say there's A, there's B. Again, we'll break it into evenly spaced units. And on this, the midpoint, where the midpoint hits the graph, we're going to use that midpoint to set the height of the rectangle. So we go up here, the midpoint's about there. So we go over, that sets the height of that rectangle. Midpoint's about there. That'll be that rectangle, and the final midpoint's about here. And this will be what we call midpoint approximation. Now, so this kind of shows you the three different ways. Right endpoint, the rectangle's heights get set by the right edge. Left endpoint, the rectangle's heights get set where the left edge meets the function. And midpoint approximation, it's where the midpoint of the rectangle meets the function, so that's the height of the rectangle. Then we add all the rectangle areas together, and that approximates the area under the curve. So what we call these, we call the spacing under each of these, and this is true for all of these different methods. The distance between each of these bits, we call that distance delta x. So the width of each rectangle is delta x. So if you think about it, if A is here, and this rectangle has width delta x, this point will be A plus a single delta x. And this point would be A plus 1 delta x plus a second delta x. So that one there would be A plus 2 delta x. Then we get A plus single delta x, second delta x, third delta x, etc. So you can keep going, and you can keep identifying these points as how many delta x's down did you count. So how many lengths of rectangles did you pass through to get to the current point that you're talking about. So what we're going to do here is we're going to write out we're going to focus on the right endpoint equation for a little bit and kind of do some work with it. And then we'll go and we'll cover the other two. So the right endpoint equation, if we think about the right endpoint equation, they use Rn to represent the right endpoint approximation. Call it Rn. If we think about it, what it does is the right endpoint approximation, we start at a plus delta x, that's going to be our x value that we start at, and we multiply it by, we don't multiply it. A plus delta x is the x value we're at. The height of the rectangle will be set of f of a plus delta x. And like the height of this rectangle will be f of a plus 2 delta x's. And so forth and so on. When you're out here at the third one, you have a delta x, a plus 2 delta x. This out here would be a plus 3 delta x's. So the height of that would be f of a plus 3 delta x. And the width of each of these rectangles is delta x. So what we get is the height of the rectangle is f of a plus delta x. The width is delta x. So the area of the rectangle would be the height times the width. So when we do a right endpoint approximation, basically what we get is f of a plus delta x, that'll be the height of the first rectangle. We multiply it by the width of the rectangle, delta x. Plus f of a plus 2 delta x's will be the height of the second rectangle. Multiply it by the width of the second rectangle. Plus so forth and so on until you get to the last rectangle, whose height would be set by a plus n delta x's. Because the little n subscript here tells us we're breaking this into n subintervals. And we multiply that by delta x. Well, if you look, all of these terms have a delta x in it, so we're able to factor it out. So we get our actual equation would be delta x f of a plus delta x plus f of a plus 2 delta x's plus so forth and so on plus f of a plus n delta x. So basically here it's height times width plus height times width plus height times width of the next one plus height times width of the next one. And that's equivalent, since all these get multiplied by the same width, it's equivalent to the width multiplying to the sum of all the heights. So we're going to do a quick example here to say how to use this equation, and then we'll probably stop there for the day. So this is just the part 1 of this thing, and we'll record the rest of it and I'll get it posted tomorrow. So for this example, we want to calculate R4, so we want 4 subintervals, meaning we want to use 4 rectangles for f of x equals x squared over interval 1 to 3. So what we got to do is, first of all, we got to figure out what's delta x. So to get delta x, that's the width of the rectangles. It'll be the interval length. So in this case, 3 minus 1 is the interval length. And we divide it by how many subintervals, in this case 4, how many subintervals we're trying to break the thing up into. So 3 minus 1 is 2, so this is 2/4, which tells me delta x is 1/2. So I get R4 equals 1/2, because delta x is 1/2. And then I get times f of A is the left endpoint of the interval, so it's 1 plus a single delta x, so it's 1 plus a single half. So that'll be the height of the first rectangle, plus f of 1 plus 2 times a half. That'll be the height of the second rectangle, plus f of 1 plus 3 times a half. That'll be the height of the third rectangle, plus f of 1 plus 4 times a half, and that'll be the height of our fourth and final rectangle there. So What we want to do is figure out what are these numbers actually, and then we'll evaluate them. F of x is x squared, so we'll substitute those numbers in to evaluate it, and then we'll multiply them all by a half. So this is a half times f of 1 plus a half is f of 1.5. 2 times a half is 1. 1 plus 1 is 2, so this will be f of 2. Plus, let's see here, this would be 1 plus 3 halves is 1.5, so that'd be f of 2.5. This will be plus, let's see, 4 divided, half of 4 is 2, 2 plus 1 is 3, so that'd be plus f of 3. And this kind of makes sense because if we have our interval and it goes from 1 out to 3 and we're breaking it up into 4 subintervals, we have 2 is here in the middle, 1.5 is there, and 2.5 would be here. So basically, we have 1.5 goes up till it hits the function, that'll set the first bar. 2 goes up till it hits the function, that'll hit the second bar. 2.5 goes up, that'll be the third bar, and 3 goes up, and that'll be the fourth bar. So we get something like that is going on for these numbers. Now to actually get them, we get, okay, this is a half. Our function f of x is just x squared. So we get, if we want f of 1.5, that's 1.5 squared. So we'd say, all right, that'll be 1.5 squared plus f of 2 will be 2 squared plus f of 2.5 will be 2.5 squared plus f of 3 will be 3 squared. And then we type this into our calculator, and it'll give us a approximation. So let's see here. We get a half. All that multiplied by 1.5 squared plus 2 squared plus 2.5 squared plus 3 squared. And that'll be pretty much 10.75. So that would be our right endpoint approximation of x squared over 1 to 3. We kind of drew a picture of what we did. So we'd say here's x squared, it looks like that. 1 is here at 1. And we'd have, say 3 is way out here at 9. We had 2 is there, 1.5 is there, and 2.5 is there. Basically what we did is we went up and we got what's 1.5 squared, and we built our first bar that way. We said what's 2.5 squared, and that would hit here at 4. So I know that this isn't to scale. We'd say what's 3.5 squared, that would be up there. Actually, let's make this look a little better, so it goes up higher, and then we say, all right, what's 3 squared? What does 3 hit this? So 3 will go up, it'll hit the function there. 3 squared is 9. And then basically what we did is we found the width of all these is a half, so it was a half times the height, that's the area of the first one, add it to the area of the second, add it to the area of the third, add it to the area of the fourth, and you sum up all the area, and all these little rectangles add up to 10.75. So we'll stop there for part 1 and pick up here next time.